Okay, so we just figured out that the product group Z mod 2 cross Z mod 3 is a cyclic group consisting of 6 elements, and we've already seen one of those in this class. It's going to be just like Z mod 6. Z mod 6 is a cyclic group consisting of 6 elements. So we saw a bit of this in my previous lecture about cyclic groups. How can we think of these two different groups as being the same to each other? How can we line up the elements of one of them to get the other? So again, my elements of the product group are 0, 0, 0, 1, 0, 2, 1, 0, 1, 1, and 1, 2. The elements of Z mod 6, oh, can you spot the typo? There are 6 elements of Z mod 6, those being 0, 1, 2, 3, 4, and 5. 6 is a residue that is equivalent to 0 here. So I actually have an extra one on my list. I'll fix that in the version of the slides I post online. If I try to squint, yeah, I guess I see a 0 and a 0, a 1 and a 1, a 2 and a 2, but these elements, I claim, are not going to behave the same way, right? 3 copies of this element give me the identity, but it takes 6 copies of this element to get the identity, right? 0, 1 has order equal to 3 in the product group, and the residue 1 in the group Z mod 6 has order 6. So I'm going to line them up a bit differently, and what I am going to do is I'm going to take my residues mod 6 on the left-hand side, and I'm going to equate those on the right-hand side with what is the residue of this number mod 2, it's going to be my first coordinate, and what is the residue of that number mod 3 as the second coordinate. So 0 becomes 0, 0, 1 becomes 1, 1, and so on. Like, for example, 5 is congruent to 1 modulo 2. 5 is also congruent to 2 modulo 3. So if I'm adding residues together on the left-hand side and comparing that to adding the pairs on the right-hand side, I'll get the same answers every single time, right? What is 1 plus 3 mod 6? You get 4. What is the pair 1, 1 plus the pair 1, 0? Well, 1 plus 1 gets you 0 in the first coordinate. 1 plus 0 gets you 1 in the second coordinate. So my idea of addition works the same way on both sides of my diagram here. Now you might be concerned, how do we know this works every single time? You know, I don't want to be writing up this table. It's all well and good for dealing with 6 things, but am I going to be doing this for a group of 120 elements? Don't really want to do that. The reason this works basically comes down to the Chinese remainder theorem. So if you think of the left-hand side as any cyclic group, and we better pick a composite modulus, the Chinese remainder theorem says I can always solve for an element that solves 2 different congruences simultaneously, as long as those residues are, as long as those moduli are relatively prime. So here, 2 and 3 are relatively prime, and the whole reason this works is from our good old Chinese remainder theorem. So in this way, I can think of Z mod 6 as factoring into the 2 different groups Z mod 2 and Z mod 3. And it's not a coincidence. That's exactly the same way as 6 factors into 2 and 3. So I would write this relationship and say that Z mod 6 is isomorphic to Z mod 2 cross Z mod 3. And I claim that this idea is going to work on all cyclic groups Z mod NZ. So if you have any cyclic group, you can break it down into smaller cyclic groups, and the moduli you get here will be the prime powers from the factorization of your n. So let's see this in general. This is the fundamental theorem of finite abelian groups. Let's say that G is a finite abelian group. Then G is going to be isomorphic to one of these product groups. Or you can just think of it as G factors into the product of a bunch of different cyclic groups, right? These are all my cyclic factors. The first one of these I've called Z mod Q1. And then I don't know how many are inside of my ellipsis here. The last one on my list is going to be Z mod Q sub K. In this breakdown, each Qi is some prime power, so P is some prime number, A sub I is some exponent. And on top of that, the representation is unique up to the ordering of the Q sub i's. So this is exactly analogous to our fundamental theorem of arithmetic. All positive integers factor uniquely into a product of primes, and it is unique up to ordering, of course, because the order of multiplication doesn't matter. Similarly here, the order of the direct product doesn't matter. You can switch your Q1, your Q2, you'll still have the same group pretty much. Now there is a caveat. Because this idea uses the Chinese remainder theorem, this breakdown does not let us split up prime powers. So here are 2 different groups consisting of 4 elements. Z mod 4Z is a group that we've been seeing for a while. It's a cyclic group, the residues mod 4. And here's another group. This is from the beginning of the group theory unit, Z mod 2Z squared. And we saw that this group is abelian, but that every single element in there, besides the identity, had order equal to 2. You can go back to my older lecture to review that. So these groups cannot be the same because this group has 1 element of order 4, actually has 2 of them, and this element has no elements of order 4. So the reason why this happens, even though it's true 4 is equal to 2 times 2, is because I can't use the Chinese remainder theorem to solve one congruence mod 2 and a different congruence also mod 2 at the same time. So there's still limits to what we can do with these kinds of theorems. But the big takeaway from today's lecture is that every single finite abelian group, it just looks like a product of a bunch of cyclic groups, and those are exactly the groups that we've been studying since the beginning of this course, even though we weren't calling them that at the time. Okay, that is all for today. On Thursday, we'll be moving on to a new unit. I'll see you then.